Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
Static equilibrium is a very important concept in the physics, and very much so in civil engineering, where we don't want buildings to be moving around or to be in the accelerating rotational motion. But how do we reach such a state? In the brief, two conditions have to be met. First, the net force on the object must be zero. So that's the first one. Most often we do this by dividing into components, so we consider the forces in x direction separately and the forces in the other directions separately. So in this case, if we have d or 2D case, we have only x and y, but of course we could have the third one there as well. And the second condition is that the net torque about any given point must be zero. About any point. This doesn't mean that we have to evaluate the torque about every single point. It suffices to do it about any single point. And you can be clever about choosing that point to make the equations easier. Let's consider these three cases where we have forces acting on these objects. So what can you say about the sum of forces in the first case? So sum of forces, it only has components the y directions to start with, so we have Fy, so that's positive, and the other one is negative, so that's zero. Okay, what about the sum of torques? We can evaluate at any given point. Of course, we do it about the center point, so it's going to be, if this is positive direction clockwise, we have F times L plus F times L, which is 2 FL. Let's make it clear. 2 FL. So the first condition checks out, the other one doesn't, or the second one doesn't. What about here? So here we have forces, sum of forces only in the y direction. We have F plus 2F, so that's 3F. So we have a problem there. The torque, however, would be if it's positive, so then it's going to be 2F times half L minus the, that's minus because that's counterclockwise, plus F times L. So torques are zero, but we have the problem with the forces. Only in this case, the sum of forces and y direction, that's going to be F plus F minus 2F. That checks out. And the sum of torques, so if we evaluate about this point, then this force doesn't produce any torque, so it's only these two. So it's going to be FL from here and minus FL from here, because that is counterclockwise. So in this case we get both conditions fulfilled. So the rules 1 and 2, they are the conditions of equilibrium, and to have a static equilibrium, we also want the velocity of the object to be 0. You can think about the case that we talked with Newton's laws. So if the force is, or net force is 0, it doesn't necessarily mean the object is at rest. But for static equilibrium, we definitely want to have that condition fulfilled as well. Here we have one such example. So we have a person standing on the ladder, and we would like to know how much friction force is needed between the ground and the tip of the ladder to keep the static equilibrium. So the forces in all directions must add up to 0, and also the torque. So we have forces in two directions, x and y. So let's first consider the x direction. And let's make our positive direction this way. And for torque, we have the clockwise direction. Both are important. But for the forces in the x direction, we have Fs, the friction, and then we have the support force from the wall. We call, well, that's of course minus, call it N1. So those two must add up to 0. In the y direction, so one more positive direction there, like this. In y direction we have the support force from the ground, so that's N2, and that is counteracted by the weight of the person, W1, and the weight of the ladder, V2. And these weights act on their respective center of masses, as we learned earlier. So these ones must also add up to 0. What else? Then we have the third condition, so those, second condition, so that's the forces add up to 0, and then the condition of net torque being 0 as well. So net torque, we choose in such a way that most of these forces, or the maximum amount of forces, cancel in terms of torque. So if we take our pivot point to be B, then the Fs and the N2, the support force from the ground, don't exert any torque. So we get the minimum amount of terms. So in that case, we only have torque from these weights and from the wall. So torque from the weight 1, it's going to be weight 1 times the lever arm, which is 1 meter, minus torque from the second weight 2 times lever arm, that's 1.5 meters. Oh, and that's positive, of course, because it's counterclockwise or clockwise. And then we have the last term from the wall. So N1 produces counterclockwise, so that's going to be negative N1, and its lever arm is 4 meters. So those must also add up to 0. And what do we have here that are unknown? So N1, N2, N1 we had already, and Fs. So we have 3 unknowns and 3 equations, so the system can be solved for all of these forces. And that is the principle for all problems in static equilibrium. You have to have the same amount of unknowns as you have equations, and not all problems are well defined, to be honest. In this case, we have a perfect match between the two numbers. For example, if there would have been friction between the wall, then this problem would have been ill-defined, and the equilibrium conditions only wouldn't have sufficed to provide a solution. And why is that? So if we would have another friction force here, let's call F wall, then this one would have only added a term to the equation in the y direction forces, and also added a term to the torque equation. So it would have introduced one more unknown, but didn't provide any new equations. And hence that system would have been unsolvable. But only way to find out if the problem can be solved is to write out these equations and try to go from there.